Hello and welcome to my paper presentation for OMSCS 6263 on how they did it, an analysis of emission defeat devices in modern automobiles. The authors of this paper are given here with Moritz Contag as the primary author out of Ruhr University in Bochum, Germany. A link to the original presentation is given here. It was given at the IEEE Symposium on Security and Privacy on May 22, 2017 in San Jose. The paper was also published in the 2017 IEEE Symposium on Security and Privacy at the given link. In this presentation, I'll first give a general overview of the purpose and problem statements from the paper. We'll then go into a lot of detail about how this problem came to be. We'll then go into two case studies of defeat devices, one from Volkswagen and one from Fiat Chrysler. And then we'll go into a solution proposed by the authors, followed by results from their testing of their solution and a conclusion. We will start with the overview. This presentation intends to show that current emissions testing methods are insufficient. There's two case studies that we'll go over of defeat devices that were used by Volkswagen and Fiat Chrysler to circumvent the emissions testing methods that are currently in place. We then go to suggest methods of cyber-physical system verification and to truly show how difficult it is and how much more work needs to be done and how much more research should be dedicated to this area. The problem is simply that environmental regulations are enforced using black box testing. They're also becoming ever more stringent and difficult to comply with at an increased cost to the manufacturer. The markets demand increased performance and efficiency, but the standards fly in the face of that because they often result in less performance and efficiency. This has led some to use defeat devices to circumvent the tests and still provide the market demands. What this means is that the environmental regulations are being broken and the environment is not being taken care of as we'd hope. Let's first go over some background info to understand how this became a problem. Software runs rampant in the automobiles of today. It's all over. One such unit that uses software heavily is the engine control unit. It reads from different sensors like the coolant and fuel and oil temperatures and actuates different things, including the emissions controls devices. One way that gasoline and diesel engines are different is in their ignition process. Gasoline engines mix fuel with air and then send them to be ignited. Diesel engines mix fuel with air to ignite them because they're in compressed chambers. This results, however, because of the complex process, in an incomplete combustion often, and thus there's higher emissions of particulate matter, soot, and nitrous oxides, NO and NO2, which we'll call NOx. And there are tight regulations on these two emissions, and so diesel engines have a particularly difficult time complying. There are several different emissions controls devices that we'll enumerate here. One that Volkswagen uses is the exhaust gas recirculation, or EGR, to reduce the NOx levels. It recirculates the exhaust back through the engine intake and burns it off. However, this increases the amount of soot, so we're left with a trade-off between how much NOx we want and how much soot we want. The ECU is used to control how much air goes back through the intake. Both Volkswagen and FCA use this emission controls device, the NOx Storage Catalyst, or NSC. It converts the NO to NO2 and then stores the NO2 in the catalyst. To burn off the NO2 to keep it clean and continue to be able to use it, the engine will switch to a richer fuel-air mixture every couple of seconds. This burns off the NO2 and increases the amount of soot. It also leads to lower fuel economy, but it does reduce the NOx levels. The final emissions controls device that we'll discuss is the diesel particulate filter. used by both Volkswagen and FCA. It reduces the soot because it traps it. However, every so often, it needs to be regenerated similar to the NSC. So we turn up the temperature by adjusting how the engine's operating and burn it off. But this comes at a performance penalty. It can also be quite the hassle for the driver. They might see this warning light in the lower right if they haven't driven at high speeds or long distances for long enough. And it will tell them that they need to start doing that. If regeneration still doesn't happen enough because it's just driven short distances at low speeds, then the DPF can fail and it'll have to be serviced. Emissions tests are performed in very standardized ways. They specify the speed at which the vehicle should go. They specify how long it should go, at which speed it's going. They even specify the test facility, things like the temperature of the test facility at the time of operation. There are many different tests in different regions, which compounds the problem of trying to satisfy them all. Emissions tests are usually carried out on a chassis dynamometer. I don't know how to say that. It holds the vehicle in place so that it can be inside a building, and yet it drives on these things that allow the wheels to turn while the vehicle stays in place. And with that, we know everything we need to know to understand defeat devices. So defeat devices are defined as a device that causes a vehicle to behave differently during a test versus normal driving. They monitor for certain conditions to determine if a test is happening, and then they take action to modify the behavior of the engine. They take a safe approach of assuming there's a test happening, and only if there's sufficient proof that there's not a test happening will they switch into normal driving mode. Now let's take a look at Volkswagen's defeat device. In September 18th, 2015, the EPA from the United States notified Volkswagen of their violation. They, in particular, accused them of circumventing emissions tests, and Volkswagen admitted to it. They admitted to cheating using defeat devices, and they paid a lot of money for it. Volkswagen's defeat device all centered around the engine control unit. They used a Bosch EDC-17 unit for engine control. This unit monitored a signal called the acoustic condition signal, and then it modified the behavior of the engine depending on the state of that signal. In particular, it modified how the fuel injection was done and the amount of exhaust that was sent into the exhaust gas recirculation unit. Volkswagen's firmware didn't actually implement this logic, they just used the parameters to make it work the way they want it to for their vehicle. The acoustic condition signal in the ECU was used to determine if we were in testing or normal driving mode. The way that the acoustic condition signal determined that was first by looking at startup conditions. If the coolant, fuel, and oil temperatures and the atmospheric pressure were within these ranges, you were said to be in testing mode. Otherwise, you were in normal driving mode, and you would stay that way. If you were determined to be in testing mode, then the rest of the parameters would be used to determine when you exited testing mode. The first one they'd look at was the accelerator pedal position. They would look at the engine revolution counter, and then finally they would look at these time to distance curves. We're going to go into more detail on what those mean. The time distance profiles had an upper curve and a lower curve that were configurable based on distance and velocity and time. They produced a curve that the ECU would check for you. The Bosch provided ECU would check this curve and check whether you were in above the lower curve and below the upper curve. Here we have an example of a curve of a time distance profile. there's two curves in here, an upper and a lower curve, and they bound the white region from the gray region. The white region is test mode, and the gray region is normal driving mode. So if your sensors indicate that you are inside the white region, then you are in a test mode, and vice versa with the gray region. What's interesting to note here is that this particularly Volkswagen specified profile fits very nicely around the time distance profile given by FTP 75, which is used in the US. It's the emissions test, one of them used in the US. Here's a second and more advanced profile that was defined a few years after the first one was. This one encompasses far more tests, as you can see by all the colored lines, and got more sophisticated because now it included a third parameter, the steering wheel angle. If it was less than 20 degrees from neutral in either direction, then you were considered to be in the white region, as long as your time distance profile also fell within it. Otherwise, you were in the gray region and you were considered to be in normal drive mode. The authors were not able to obtain much of their data directly from manufacturers. The data wasn't provided directly by manufacturers, but the performance tuning community does get a hold of these things, how these engines work, and so these data sheets were provided by them. This function sheet in particular was obtained for the EDC 17 dated December 2009. And it is copyrighted by Bosch. They added the blue shaded regions and the blue numbers. What this logic diagram shows is how the acoustic condition signal gets calculated, and we'll go into detail about each section. This first flip-flop, number 1, highlighted by the green arrow, stores the state of the acoustic condition signal. It's the result of all the logic that's gone before it. If the flip-flop is set, then we're in testing mode, and if it's reset, we're in normal driving mode. This logic at number 2 is the logic that checks those startup conditions, the temperature of the coolant, oil, and fuel, as well as the atmospheric pressure. So the flip-flop is only set if those conditions are within their desired ranges. Otherwise, the flip-flop can never be set, and thus the acoustic condition won't be set, the acoustic condition signal, and so we will be in normal driving mode. There is a flip-flop tied to the reset signal of flip-flop number 1, and that's this flip-flop, number 3. So there's some extra conditions that are allowed if at startup we are detected to be in testing mode, and this flip-flop controls those extra conditions and can reset flip-flop number 1 in order to change us to normal driving mode. This logic monitors 3 things. The position of the acceleration pedal. Once it's exceeding a certain threshold, there's a timer that will count down, and once that expires, the flip-flop will be set at number 3, which will change us to normal driving mode. It also monitors the engine revolution counter, and once that has exceeded a certain threshold, flip-flop number 3 will be set. The third condition is not used. The blue section below was not included in 2007 diagrams. It was only added in 2009, and I'll talk. This logic, highlighted by the arrow on the blue region and the number 5, is the section of logic that monitors the time distance curve profiles, as well as the steering wheel angle. These profiles must all be set. Each flip-flop must be set, so each flip-flop ties to a certain curve, and there was up to 7 available at first. They moved to 10 later, but there were 7 available profiles that you could match against. If the parameters ever moved outside of the curve, the flip-flop would be set. And once all flip-flops were set, then the signal to number 3 would be set, which would thus reset flip-flop number 1 and change us to normal driving mode. This diagram, obtained from the EDC 17 function sheet, same as the other ones, is also copyrighted by Robert Bosch. What it shows is the calculation of an additional quantity that is a correction quantity for the fuel injection amount. This integrates our acoustic signal. So this here is the same name as the other name for the acoustic signal. This is an input. So if the acoustic condition is set, one set of things happen, and if it's reset, a different set of things happen. If it's set, this Q core value is held constant at a configurable value. And this was used to have less exhaust emissions, because this was done in testing mode. If the acoustic condition signal was reset, then we were in normal driving mode, and it actually switched to using the logic next to these green arrows. These would choose the Q core value based on the current engine speed. So they quit worrying about exhaust emissions and they worried about performance. This logic is actually quite complicated, and we're not going to go into a lot of detail, but it shows how the acoustic signal was used to influence the exhaust gas recirculation amount. So this was again from the function sheet copyrighted by Bosch for EDC 17, and the blue region was added by the author. This blue region highlighted by the green arrow shows the acoustic condition signal. It's the exact same name. What it was doing here is it was influencing what set of parameters were going to be used in calculating the correction value for how much air mass would be fed into the EGR. Thus, in testing mode, one set of parameters were used that would allow more air into the EGR and thus clear up more of the emissions than in normal driving mode. So that was one defeat device used by Volkswagen. This one used by Ford Chrysler was quite a bit simpler. So on February 2nd, 2016, just shortly before this paper was written, FCA issued a statement. It was a bit after Volkswagen. They issued a statement claiming that they had not violated any emissions tests using software. Then on February 9th, a week later, the German Environmental Protection Organization accused them of exceeding the emissions limits on one particular model of SUV. About a year later, the US EPA formally accused FCA of using defeat devices to cheat, just like they had done with Volkswagen. They never admitted to wrongdoing, but about a month ago, in May of 2019, FCA reached a settlement and paid a fair bit of money to end this. So let's go into detail on what the authors think was their defeat device. So FCA used the exact same ECU that Volkswagen did, the Bosch EDC 17, but they didn't use the same technique as Volkswagen. Instead, they focused on reducing the frequency of the NSC regeneration, the NOx storage catalyst. But they waited for a bit of time before they started reducing that frequency. So it was quite a bit of a simpler approach. Remember that NSC burns off more NOx, and so it increases soot. So in order to reduce that level of soot and reduce the load on the diesel particulate filter, they increased the amount of time between regeneration. This also improved the fuel economy, but it did increase the NOx levels. As with Volkswagen, FCA simply used a function block that was already provided to them in the ECU. They simply tuned a few parameters. The blocks that were provided to them were two parallel methods of requesting an NSC regeneration cycle. One was titled the homologation cycle block, and one was titled the real driving block. There were separate calibration parameters for each block, and each block had the equivalent ability to request the regeneration cycle, as I said, but the homologation cycle could be turned off. Just for reference, homologation refers to the process or act of granting approval by an official body. So these were very clearly titled with their intent to be able to circumvent testing by an official body. So the two parameters that allowed the homologation block to be disabled were, one, the amount of fuel used, and two, the time since the engine had started. So what FCA used in their firmware that the authors analyzed was 1.3 liters for the amount of fuel. That's about a third of a gallon, so not a lot before the homologation block was disabled. The time since the engine was operating parameter was 1600 seconds, which is 26 minutes and 40 seconds, which coincides precisely with the standard emission test cycle time. So they would delay it for 26 minutes and 40 seconds and then turn off the homologation block. What happened is the homologation block and the real driving block would both trigger NSC regeneration cycles at different frequencies, but then once the homologation block was disabled, then only the real driving block would be triggering the regeneration cycles, and so there was a decreased frequency of regeneration cycles after that. So now we understand how those two defeat devices work, which allows us to go into the proposed solution. The authors proposed a static analysis tool as the solution. It analyzed their firmware. They wanted it to be automated so that they could cover a lot of firmware without much work. They wanted it to be static because it was difficult to run the firmware in an emulation environment, and because they wanted to get higher code coverage than dynamic analysis might be able to achieve. Their solution was called CurveDiff, and it was specific to the EDC-17 ECUs that were used both by Volkswagen and Fiat to do their defeat devices. What it did is it focused mainly on determining if the software was checking for time distance profiles like Volkswagen did. They didn't do a lot to try and detect the Fiat Chrysler defeat device. So the basic steps in their static analysis tool were first to run a disassembler and then pre-process that disassembly with a lot of complicated ideas, and then to look for the curve function invocations. They would look for the specific functions that were looking at the parameters that were used in the curve functions. And then they would try and correlate those curve function invocations to find the curves that they were trying to grab, and then correlate those curves with known emissions test profiles. Let's talk about what they found. With their software, they analyzed 963 firmware images. A little less than half were found to be using a defeat device, just using it. But 333 were found to actually test against an emissions test profile. There was 39 that failed because they timed out because they didn't want to wait too long. So they set a timeout, or otherwise they failed. The performance, they were able to analyze one piece of firmware in 55 seconds. That was the fastest. several timed out, and so it was slower than 7 minutes. And the average binary was analyzed in about a minute and a half, which is much less than current emissions test times. The types of static analysis tools that the authors presented here were really limited in scope to active types of defeat devices, those like Volkswagen that monitored current conditions to determine if there was a defeat device. CurveDiff was good at detecting these. However, FCA used a more passive type of device that just had a fixed time delay. CurveDiff would have a hard time at detecting these sorts of defeat devices, and further enhancements were needed. However, these automated tools need to be developed and used in testing. Automobiles are becoming more software-centric, and incentives are becoming greater and greater to cheat on the tests as they become more stringent and difficult and costly. And so these types of tools need to be employed in testing. They'll shorten test time, they'll be more accurate in finding emissions non-compliance.